All right, so yes, test Friday. You'll again have an hour and 45 minutes, starting at 9 o'clock, going until 10:45. What's on the test? Well, certainly all of Chapter 1. And the first section of Chapter 2, certainly. We're going to start that today. Maybe a little bit of the second section of Chapter 2. We'll see where we get to by Wednesday. Again, the exam is mostly written. However, I am not quite done with it. There'll be one or two more questions that I'm going to add to it. I didn't do those questions over the weekend because I was busy writing another exam that I'm actually giving today in multivariable calculus. So I wasn't able to do that. I also wasn't able to finish writing the third extra reading assignment yet. I will try to finish that today and post it on Moodle. The length of it, again, is not quite as long as before with the first two, but it's still challenging material. All right, today's going to be kind of a theoretical day. All right, we're going to talk about a certain kinds of proofs. There are not going to be any proofs on this first test, but there probably will be on the second and third tests. And the proofs on the second and third tests will be somewhat similar to the things we talked about, at least a particular kind of proof that we do today. So we're going to talk about proofs. We're going to talk about why integrating factors, why that method works. And we're also going to talk a little bit about physics as far as an application goes. But we'll talk about it in a general setting of a mass and a spring, obeying Hooke's law. All right, so let's start by just considering an arbitrary-looking linear differential equation that's also homogeneous. So dy dt equals a of t times y. There's your generic form of a first-order linear differential equation. It's also homogeneous. There's no b of t. There's no plus b of t here. It's also separable. And you should, anytime you see something like this, you should realize that it's separable. We can bring the t's, the y's to the left side and all the t's to the right. We can write this as dy over y equals a of t dt. And then you can integrate both sides. You're going to get a natural log of the absolute value of y on the left, though I will dispense with the absolute value symbols. And you'll get the integral of little a of t dt on the right side. And then when you exponentiate, you can write your general solution in this form. Although with the caveat that, this integral is going to end up giving you some antiderivative of a of t plus c, and then you separate out the c to be also a power of e, e to the c times e to that antiderivative, and you could replace that e to the c with some other c, and that other arbitrary constant can be both positive and negative. I want to do something different here, though. I want to think of that as being a particular antiderivative, and that's going to make this not a general solution. Call it capital A of t. That's usually kind of a tradition in calculus to call it antiderivatives, the corresponding capital letter. And let's make the graph of capital A go through the origin. Capital A is not a solution. This function is a solution. E to the capital A is a solution. In fact, since capital A of 0 is 0, and since e to the 0 is 1, this solution is going to satisfy the initial value problem where y of 0 is 1. That would be the initial value problem this function would satisfy. That's a solution. That's not. It's just a way of helping us write the solution. Certainly you can check this is a solution, no problem. And again, I'm saying this is not the general solution. This is just one particular solution. You can check it by differentiation. The left-hand side of the differential equation is dy dt or y prime. By the chain rule, you're going to get that. That's the chain rule. And since capital A of t is an antiderivative of little a of t, this derivative is going to be people who eat their eyes open.
Lowercase a of t.
Lowercase a of t, yeah. I know you can watch it later when you're feeling more awake, but I'm going to try to keep people awake here as best I can. I'm going to try to ask lots of questions. What about the right-hand side of the differential equation for this function? The right-hand side is a of t times y. What is y? In this case, y is e to the a t, e to the a of t. So you do get the same thing in the end. The left-hand side does equal the right-hand side after simplification. Can I clarify anything there? It's abstract. I don't have particular formulas there, but this is kind of an abstract line of thought you should be able to deal with at this point. But I want to do something else besides checking that it works. Two other things, actually. I want to show that if I multiply it by any constant, let me actually give it a name. Let me call it y sub h. It's not the general solution of this homogeneous equation. It's a particular solution, but the following calculation justifies that if I multiply that function, that one function, by any arbitrary constant, like the book, I'll call that constant k this time. That's an arbitrary constant. If I multiply this particular solution, yh, by an arbitrary constant, I get another solution. YH is the solution that we just wrote down. I'm not bothering with the t there. YH does depend on t, k doesn't. Keep that in your mind. By linearity of differentiation, what do I mean when I say that? What's linearity of differentiation here?
You get constant times the function of the thing you're differentiating by is equal to the constant times the derivative of that.
Right. It's kind of like a distributive property. Not exactly, but kind of like that. It's like you can factor the k out. You can write the derivative that way. Yeah. The derivative of a constant times a function is the constant times the derivative of a function. And since yh solves the differential equation, I can replace that derivative with a of t times yh. Maybe I should put a t there since I've got a t there. You don't traditionally write it in the differential equation in place of the y, but maybe I should put a t there just for clarity. And then it's just a matter of rearranging. Switch around the a of t and the k, and keep the parentheses around the k times the yh. And maybe to be consistent with this, I won't bother putting the t there. So here I'm being sloppy. I'm not putting the t there, but I am there. Okay. Don't worry about it. That kind of thing here is not a big deal as long as you keep it straight in your mind. This does emphasize that k times yh solves the differential equation. Okay. It's not really a proof in the kind of way that I'm going to want you to ultimately do on tests or on homework, because with proofs on tests and homework, you really should write the sentences. I'm just trying to get the idea across. You might want to make notes to yourself about what idea I'm trying to get across. I'm trying to get across, in this case, the idea that if you got a solution of an equation like this, then any constant multiple of it is also a solution. It's the linearity of the equation that allows that to work. If I had a y squared there, and said yh solves that, and you're wondering whether k times yh solves it, I would have gotten a square there, and a square here, but that would have been a problem because the k would not have been squared, which it would need to have been in order for k times yh to be a solution if it had a y squared in the equation originally. These calculations are also out the window, but as far as this abstract calculation goes, it also would not work. I don't have a square there, so I don't have to worry about that. Okay, so again, the point here is any multiple of a solution, any scalar multiple, constant multiple, whatever you want to say, of a solution is also a solution. But there's something even more subtle going on here that we need to think about. When I say this is the general solution, k times yh, I mean not only is it a solution, but all solutions can be written in that form, which is a slightly different question. How do you know, given any arbitrary solution of the original equation, that there's some constant k where this is true, where the function, the solution equals k times yh, is what I mean by this is true. That's a different issue. Probably better write some words this time. Given any solution, what should I call it? I guess I'm avoiding the fees for the moment. Y G? That's probably a bad letter. I'm just thinking of a letter near H. The G doesn't really stand for anything.
C.
C? Maybe I should call it YL, that's an L, for linear. I don't know. Given any solution YL, write the L like a cursive L to make it clear that it's an L, but don't make it too small because then it looks like an E. Given any solution YL of this equation, is there a constant K so that YL equals K times YH? That's the question I'm trying to answer now. For all t. You don't see any t's here? It's just in your head? Being sloppy? Saves a little time. Be sloppy as long as you understand that y, h, and yl are functions of t and k is a constant. Well, what would this kind of equation be equivalent to? YL equaling k times yh would be equivalent to YL divided by YH always equaling k. Assuming we're not dividing by 0 there. I guess I'm implicitly assuming YH of t is not the 0 function. I'm never dividing by 0. In fact, let's just go ahead and assume it never equals 0 for that sake. Just to think about it this way. Actually, 0 is an equilibrium solution of this equation, even though it's non-autonomous. You can still have an equilibrium solution for non-autonomous. You just don't usually have equilibrium solutions for non-autonomous. But this one's got one. Y equals 0 is an equilibrium solution. So really I'm thinking about a non-equilibrium solution, and that will never equal 0 because of uniqueness, assuming a of t is a nice function, which I am implicitly assuming. So YH of t is never going to be 0 because I'm not considering the equilibrium solution at 0. So the goal would be to show that this ratio is a constant no matter what t is. Again, these are functions of t here. How do you show a function's constant with calculus? You want to say that?
The derivative is 0.
If the derivative is always 0, you can apply something called the constant function theorem that says if the derivative of a function is always 0 over an interval, the function must be constant over that interval. That's actually not easy to prove, even though it sounds so reasonable. If the derivative is always 0, the function is always constant. Actually, if it's over two separate intervals, the function can be piecewise constant. It doesn't have to be constant over the same value of the constant over the entire combination of both intervals. So what I should do is I should differentiate this ratio, YL divided by YH, and see if I get 0. How do I do that? Well, first of all, how do you differentiate a quotient? Quotient rule, yeah. Get the first term right, low D high. Start with the low. Low, D high, I'll just use primes. The bottom times the derivative of the top minus the top times the derivative of the bottom over the square of what's below over the bottom squared. Is that helpful? Want to show this equals 0? Do you have a guess about what to do here? That's what we hope to show. I don't want to set it equal to 0. I'm not trying to solve for anything. I'm trying to show it equals 0. What have we not used yet about YL and YH? YH is this particular function, by the way. It's the same function as before. Question? Or?
Is it just that YL equals KYH?
Yeah. Oh, well, excuse me. Sorry. I jumped ahead too fast. That's what you were trying to show.
Is that what,
Right
like,
above it.
did you just like plug that in though and then like show them if it cancels?
Well, you're trying to show that. You'd be assuming what you're trying to show if you do that.
Oh, the derivative of YL is A of T Y.
Yep, times YL. YL and YH solve the differential equation. So use that fact. That means YL prime is A of T times YL. That's what it means to solve the differential equation. Okay, again, the YH and the YL depend on T. I really should put T's to the right of them too, but I'm being sloppy. Just be okay with being sloppy. As long as you understand. YH prime solves the differential equation as well. We already knew that. So YH prime is also A of T times it. A of T times YH. And lo and behold, we get cancellation. Those two things always cancel. This equals 0 for all T. Defined for all T actually as well, as long as the A of T is nice and defined for all T. That's going to mean this ratio is a constant. There's some K that it equals for all T, which is exactly what I want to show. Okay, that's pretty tricky. Probably if I put one like that on the test, which I probably will not, I'd have to give you hints. So what type should you be able to do on the test? Well, the other one that I just erased there before, that was here before, this spot, you should be able to do that type, showing a constant times a solution is also a solution. You should also be able to show what I'm about to show you. Let's now consider a nonhomogeneous equation. So put a plus b of t there, where b of t is not the 0 function. It, of course, still has the associated homogeneous equation. Where you get rid of the b of t. What's my goal here? I really want to show that if I take the general solution of the corresponding associated homogeneous equation, YH, which you can think of as constant times a particular YH, or you can think of the YH as already having the arbitrary constant in it. And if I add a particular solution to the original non-homogeneous equation, then I get a new solution, and in fact, ultimately the general solution of the original non-homogeneous equation. You did that with the guess and test method of undetermined coefficients. That's the kind of method you used. Found the associated one, found the YH from that, found a YP, a particular solution to this one by guessing, and then added them together to get the general solution of this. I'm going to say let YP and YQ both solve that non-homogeneous equation. I claim that YP minus YQ solves the associated homogeneous equation. And I claim that's also enough, in addition to what I showed already, to prove that YH, either including an arbitrary constant in front of it, or already including an arbitrary constant in its formula, plus YP, is the general solution of this. Why does showing that this difference solves it? I'll explain that in a minute. But let's just show that this solves this. I'm going to add a few words here. You should include words like this in a proof. By linearity of the derivative and our assumptions. What assumptions? That right there. Probably shouldn't draw a bunch of arrows in a proof though. I'm doing it in class to hopefully make things more clear. If I differentiate YP minus YQ, I get YP prime minus YQ prime. That's the linearity. Linearity also applies to sums and differences. In this case, the derivative of a difference is the difference of the corresponding derivatives. And I'm assuming YP and YQ both solve this, so I can replace those derivatives with the right-hand side of the differential equation with YP and YQ plugged in for Y. And again, there's a T in the background, but I'm not writing it for sake of time mostly. So my arm doesn't fall off from being too tired writing too many T's. YP prime, well, I guess I better put the A of T and B of T in there with T's. YP prime always equals A of T times YP plus B of T. Putting the T's in there for the A and the B. Not bothering with the YP, but it's there in your mind. Minus YQ also is assumed to solve the same differential equation. So its derivative always equals this for all t. You get cancellation of the B of t's here, and lo and behold, the terms that are left both have a factor of A of t that by the distributive property can be factored out. And you can rewrite that as A of t times YP minus YQ. By the distributive property, if you want to add a little phrase at the end. That is the actual distributive property. And again, this is true for all t. What have we shown here? What does this mean? The derivative of that function is A of t times itself. What does that mean?
That it solves the associated homogeneous equation?
Yeah, that it solves this. It's a function whose derivative is always equal to A of t times itself. And that means by what we proved, what was it, 5-10 minutes ago, that this difference must be k times YH. If I'm thinking of YH being a particular function, one particular function, k times YH is the general solution of the corresponding homogeneous equation. Since I showed that this function also solves that equation, but by what I proved before, that means it's got to equal k times YH for some k. So yp minus yq does equal that. So yp equals kyh plus yq. Maybe I should have switched the p and the q around actually, and said yq equals k times yh plus yp. What this is showing is that if yq is one particular solution of the original non-homogeneous equation, then any other solution of the original non-homogeneous equation must be in this form, which justifies writing this type of thing as the general solution of the non-homogeneous equation. And again, I probably should have switched around the roles of yp and yq, since we usually put a yp over there. But the idea is the same. So this is pretty abstract stuff. It definitely takes some thinking. It definitely takes clarity of really understanding the concepts, understanding what it means to solve a differential equation. Don't just put this away in your notebook and never look at it again. Spend time thinking about it. We will do more proofs of a similar type, I think in chapters 2 and 3, and probably there will be one proof of a similar type on the second test. Oh, things always take longer than you think. Let's go on now and think about integrating factors, and think about why that works. So again, this is kind of a day where we focus on theory. Not that, to emphasize that theory is important, okay? The theory is what justifies the techniques. When you write proofs, you should write in sentences, just like you do on the graded assignment. Proofs are arguments. Arguments are written in complete sentences. Your equations can go in the sentences and be part of the structure. And it's not that you can't separate equations out in separate lines, but it should be part of the sentence structure, just like in your graded problems. But for the sake of time in class, I don't always write sentences, because we've got a lot of things to talk about here. And the next thing is the idea of an integrating factor. It applies once again to the same kind of equation, a linear equation, linear in y, linear in its derivative as well. The a of t and b of t can be nonlinear functions. It's still a linear equation. Though we typically, for the method of integrating factors, write it in this form. And in fact, change that slightly to look like this, where g of t is really the opposite of a of t. What's the big idea with integrating factors? Well, it's a function that ends up being a factor, a thing you multiply both sides of this equation by. Doesn't matter what you call it, but it is traditional to call it mu of t. So multiply both sides by mu of t to get this. Don't forget to do it to the right side. That's a common mistake. People forget to multiply the right side by mu as well. You do want the new equation to be equivalent to the old equation, assuming mu is never 0. It looks more complicated, but if that expression right there happens to equal mu prime, if you choose mu so that that happens, want this to equal mu prime of t for all t. If that is the case, what does that mean? It means the left-hand side is mu, a function, times the derivative of the solution you're after, plus the derivative of mu times the solution. It's in the form of the product rule. if mu prime of t does in fact equal mu of t times g of t, then you can rewrite the equation as mu of t, I'll just use primes now for the y as well, times y prime plus mu prime of t times y equals mu of t times b of t. I could put t's by the y's, but I'm not doing that because it's traditional not to. Sometimes it's to save writing, sometimes it's just tradition to not bother, in this case, putting t's by the y. This thing right there is, by the product rule, the derivative of mu of t times y, where again y does depend on t, but I'm not explicitly writing it. Y is the solution you're after. It's the function you're after. If mu does satisfy that, so that this equation can be rewritten as the derivative with respect to t of mu times y equaling mu times b of t, then you can just integrate both sides. The left-hand side is easy to integrate because it's the derivative of a function. So its integral is just the function. The plus c, again, could be thought of as just going on the right side. Mu of t times y equals the integral of mu of t times b of t. I did integrate the left side there. You want to solve for y, so in abstract form you can write the solution as y equals 1 over mu of t times the integral of mu of t times b of t. Though in practice, you want to make sure you do the calculations correctly and calculate the integral if you can. But why does that strange formula for mu work? Why is it e to the integral of g of t? Well, if you want this to be true, that means mu itself satisfies a differential equation. Its derivative is always equal to itself times this function g of t. Mu satisfies the equation d mu dt equals g of t times mu, which is separable. It's just like the nonhomogeneous equation here. Excuse me, homogeneous equation. It's the same kind of thing, same kind of idea. The derivative of an unknown function equals some function times itself. You can separate variables, bring the mu on the left side, bring the dt on the right, integrate, get a log of mu equaling the integral of g of t, then exponentiate to get rid of the log. And you can check it with the chain rule too, by the way. The derivative of this, if you think about it, by the chain rule is e to this power is mu itself times the derivative of the integral, which is g of t. So you get mu times g of t when you differentiate. Don't let it bother you that there's an integral in the exponent. Sometimes in math you just got to get used to things. It's written as an arbitrary antiderivative there. And yeah, you can use any antiderivative that you want, though you usually try to pick the simplest one. Pick the one that goes through, whose graph goes to the origin, just like we picked the capital A to have a graph that went through the origin. A of 0 was 0. So you want to pick one particular antiderivative there for G to create mu. All right, so in a nutshell, with these equations and my verbal explanations, that's why it works. Or at least that's why it's plausible that it works. And you should understand this. Probably not going to put anything on the exam where you have to explain this, but I really do think you should spend the time understanding it. To understand that integrating factors, even though it kind of seems like magic, it's not, okay? It's based on some things that are logical. Main places people make mistakes, are forgetting to multiply the right-hand side by mu as well, and then just sort of not realizing that that thing is the derivative of mu times y. Once you realize that, if you pick mu correctly, then it's easy from there. You still have to do this integral, but otherwise, up after that point, the idea is pretty clear. All right, a little bit more abstract stuff. We're going to go back to the extra reading and the flows. Thinking about this through examples, I am going to put this stuff on the test. Did I say I was, or is that something that I didn't say? I forgot. I forgot if I wrote it on the test yet or not. I think I did. I think I said that in the email. If it's not one, then I will put it in there. I believe I already put it on there, though, on the test. Okay, essentially this flow idea is just an alternative way of thinking about the solution, initially at least. And ultimately what you're trying to do is you're trying to relate the solution to iterating a function, applying the function over and over again. It only works for autonomous equations. The formula can work in a non-iterative way for non-autonomous equations, but if you want the iteration of this function, this flow map, to match what's happening to solutions, the differential equation needs to be autonomous. And in the reading, there are non-autonomous examples, and you see that it doesn't work for those. It's also nicest if the solutions as functions of t don't have any vertical asymptotes. If they do, then you have to consider smaller values of t when you iterate this function. Those kind of examples come up in the reading as well. In class, I want to focus on the simplest examples, and on the test, it'll be a simpler example type. Probably one of these types that I have for today here. 2 examples for today. We looked at this example already. Simple differential equation, dy dt equals negative 2y. You could think of that expression right there as defining the general solution if y was an arbitrary constant. On the other hand, you could also think of it as defining a particular solution to an initial value problem if y was a fixed constant, like that we typically call y sub 0. This expression would define a particular solution in that case as well. But now I'm thinking of it differently. Now I'm thinking of this expression as defining a function of y for any fixed t. And as a function of y, it's a really simple function of y. It's linear. And its graph goes to the origin. And its slope is this number, which when t is fixed is a fixed number, e to the negative 2t. Again, this code will plot it as a function of y. The horizontal axis there is labeled with a y. Different t's give you different lines. And what's the important point about this? How is it related to the differential equation? The most common thing to do when you don't have to worry about vertical asymptotes is to pick t to equal 1. To consider what's called the time 1 map. So your general formula here is phi of t, phi t, it's not a power, it's just a label, it's a superscript that's a label, though we put it up there because it kind of acts like a power in ways I haven't described yet. Here again is the formula for it. I can pick specific values for t, like 1 is the most common thing to pick, to get a specific linear function, e to the negative 2 times y. So when t equals 1, t equals 1, that graph right there has a slope of e to the negative 2, which is, I don't know, going to be between 0.1 and 0.2 for the slope there. Y increases by 2 here. Oh, when y increases by 4, the vertical change is close to 0.5. 0.5 over 4 is 1/8. Okay, I think e to the 2 is 7 something. So e to the negative 2 is 1 over 7 something. That's the slope of this line. If I pick a fixed value of y, and I can pick anything I want for y, pick 10, and plug it into this function in place of y, get 10 times e to the negative 2, that will match the value of the solution of the IDP where y0 is 10 at time 1. This is also the value in our other notation of that. The unique solution with initial value 10 at time 1. Now that would work even if the equation was not autonomous. The key thing about this being autonomous is that now you can continue following what happens to 10 for the solution curve if you iterate this function right here. If you apply it over and over again. That's the key with autonomous equations. And that's the main thing I'm trying to get across that I want you to know. If you iterate this function, in this case, what are you going to get? You're going to get that, and ultimately, plugging e to the negative 2 times 10 into this equation in place of y, you're going to get another factor of e to the negative 2. Which ultimately simplifies to e to the negative 4 times 10, which is the value of the solution, the unique solution with initial value 10 at time 2. Which makes sense, because you just plug it into this formula, thinking about it as defining a function of t when y is fixed at 10, plug in t equals 2 into there, and you're going to get that. Again, the key thing about the autonomous nature of this is that this iteration of phi1 that will still make a match. And that doesn't work for non-autonomous equations. You can look at the examples in the reading. You'll see that it doesn't work. I'm not going to take the time, because we're running low on time, to do that in class. That could be maybe another thing that I add in the test a little bit, is consider a non-autonomous equation where you can go ahead and define an expression like this, but iteration of it does not really follow solutions like you want it to. See that in the example. Here's another example. Well, by the way, you can iterate functions like this with NestList, and that's what this code does. This is iterating this time 1 map with initial condition 10, value y at 10, and 5 iterates. And I should also say, by the way, that you can visualize these iterates nicely on the graph. This is called a Cobweb diagram, though it doesn't really look like a cobweb for this example. If you plug 10 into this function, this is phi1 of y equals e to the negative 2 times y. This is a y-axis here. Plug in 10 to the function. The output is e to the negative 2 times 10, which you can think of as being the second coordinate of both of these points, which also, because this line is going to be the 45-degree line going through the origin, this point is going to have a first coordinate equal to e to the negative 2 times 10 as well. And so to find the next value, you can, instead of going all the way down to the y-axis here, just go down to the graph of the function you're iterating and continue going back to that diagonal 45-degree line. To be more specific, the second coordinate of these 2 points is e to the negative 4 times 10, which means the first coordinate of this point is e to the negative 4 times 10. And this staircase process in this example shows you visually how the iterates in this case are heading towards 0. Just like if you drew the phase line for this equation, 0 would be a sink. And that's why those iterates are heading towards 0. The phase line for that differential equation, right there, has one equilibrium point at 0, and it's a sink. And that's why these iterates are heading towards 0. The solution curves are heading towards 0. The outputs of the y values along solution curves are heading towards 0. Just like we're seeing here. These numbers are getting closer and closer to 0. Another example is right here. Once again, it's autonomous. What's the flow in this case? Well, we could use d-solve value. In fact, I already had it there. D-solve value and expand can be combined to get this expression for the solution if you think of it as a function of t. But now for the flow, you think of it as a function of y, and replace the y0 with just a y. This will become 5/3, well, I could write it like this, times 1 minus e to the 3t plus e to the 3t times what? I'm looking at this expression, rewriting it a bit, and replacing the y0 with a y. That's a linear function of y as well, at least linear in the usual sense from pre-calculus. The graph of that as a function of y is also a straight line, because it's a constant, t is a constant here, times y plus another constant. The graph of this is going to have a slope of e to the 3t and a vertical intercept equal to that. Again, for fixed values of t. Graph quick here. Need that other piece too here. So we get, again, 5/3 times, in parentheses, 1 minus e to the 3t, and then plus e to the 3t, times plus e to the 3t times y. Think of that as a function of y. It's got a straight line, graph is a straight line through the origin when t is 0. When t is 0, it won't go through the origin. It's not 0, I mean. So for non-zero values of t, not only do you get a different slope, but you also get a different vertical intercept, as you'd expect. This is the vertical intercept right there. And again, iterating this function tells you things about solutions. In this case, what happens to the iterates? I'll use NestList here. I can use 10 as the initial condition again. Yikes. This time, the iterates go off to infinity, it seems. Which is not surprising, because this is a positive coefficient for the y. The equilibrium solution is going to correspond to a source on the phase line. If you drew the phase line, yeah. The equilibrium solution at 5/3 would be a source. So it's not surprising that these go off to infinity. Oh, I want to do some physics today. All right, we don't have time to do the physics. And I know even with this stuff I went fast, okay? So you may want to watch the video again, especially if you were falling asleep on the proofs. Listen very carefully to the things I say. I'll leave the physics reading and actually some competing species models to you. There's a completion assignment due Wednesday, and there will just be a completion assignment due Wednesday, no graded assignment, related to section 2.1. I do have those optional videos that you can look at as well that do address those things. Okay? See you Wednesday.